Hello, good evening to all. So, welcome to this first lecture of this lecture series on Introduction to Basic Electronics. So, in this particular lecture, I will start with the basic fundamental and I will start with the current because current is the key element of all the electronics and the electrical devices, and it is mainly the current that we need to control. So first of all, I will discuss how the current is generated, and thereafter I will go to the atomic energy level, means the atoms, and how the energy levels are created from the single atom, and thereafter the combination of atoms to form the energy bands, and then how these energy bands differentiates between the conductors, insulators, and semiconductor, and how this energy band gap, what is unique in the energy band gap that makes these semiconductors, like that makes semiconductor with some capability that is not there within the conductor and the insulator. And at the end I will then introduce the intrinsic semiconductor material, right? So starting with the current. Now we all know, like from our school time, we all know that the current will be there whenever there is a flow of charges, and the charges, it can be the positive charge or the negative charges. And we also know that if the suppose if current is in the, or if electrons or negative charges flow in this direction, then the direction of the current will be opposite to the flow of electrons or the negative charges. Whereas suppose if we have some positive charges, then the, and if the positive charges, like positive charges, if the positive charges are flowing in this direction, then the direction of the current will also be in the same direction, right? So it means that the direction of the current and the electrons, they are opposite to each other, whereas the direction of the current and the positive charges, they are in the same direction. Now one question may be arised, what are these positive charges? Because we all know that electrons are free, and it is mainly due to the flow of electrons that current is there. Then why we are talking about the positive charges? And in electronics, like quite often we are going to talk about the positive charges. Now positive charges, when we talk about positive charges, then remember that positive charges can also be understood as absence of electrons, absence of electrons in the atom. So suppose if in particular atom, it is, if it is supposed to have 17 electrons, if a particular atom is supposed to have 17 electrons, right? But if somehow if one electron is taken out, so at the end it left with 16 electrons, right? Now there is an absence of one electron, and that absence of one electron, we can say that there is a space for the positive charges. One absence of electron, it is equivalent, one absence of electron, it is equals to one positive charge, right? So remember this, because whenever in electronics, whenever we talk about the positive charges, flow of positive charges, as such there are no positive charges, and this positive charges, they are just a virtual term. As such, they does not have any real existence. It is only that it, with positive charges, we means the absence of electrons, and only if the, like if suppose if at this location if there is one electron missing, and now, so it means over here we have a positive charge. But now if this positive charge means the absence of electron, if it receives some electron from this, from the neighbor, then if neighbor contribute its electron to the positive charges, it means that this neighbor will now be deficient of one electron. This neighbor will have one less electron, so the positive charge will just flow from this location to this location, right? So in this way, the absence of electrons can also flow. Now one more thing that is important to know about that, in the difference between the electronics and the electrical, Now in electronics, like in electrical, like we need heavy currents, because in electrical, whenever we talk about electrical devices, for that, like electrical devices like fan, like tube lights, like TV, so for that we need huge amount of current, right? Whereas when we talk about the electronics, it is mainly we need current just for the computation, for some sensors, for some sensing something, right? So we do not need to run anything, we just need to process, we just need to sense. So very little amount of current is also okay for the electronics. So it is the reason that we in electronics we are not going to talk about a high current, we will just talk about the low current, in fact the very low current, right? And since we are talking about the very low current, so we need some devices where we will have less losses and where we can control the current as per our requirement, and that control can be done with the help of the semiconductor devices. So right, and the chlorine, it has 17 electrons in the outer like it has total of 17 electrons, and we already know that as per the Bohr models that the first shell, it will have 2 electrons, the next shell it will have 8 electrons, right? 8 electrons, and then means 8 2 8, 2 plus 8, it is 10. So now we left with only 7 electrons. So it means in the outermost shell of this chlorine we have 7 electrons, right? Now if we talk about the energy, if we just draw a diagram between the energy level and the shell, right? So the if we talk about this first shell or the innermost shell, so since these electrons they are tightly bounded to this nucleus, right? So they does not have any energy to move, they cannot move, and since if they cannot move, it means they are stable, they have very 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 low energy, right? So we can say that the energy of the first shell or the innermost shell, it is the minimum, right? And if we talk about the second shell, this second one, if we talk about this now, this electrons in the second shell, they are also very tightly bound, but in comparison to the electrons in this first shell, they are little bit less tightly attracted with this nucleus, right? So the energy level, like the energy of the second shell, it will be little bit higher than the first one, right? Now if I talk about this third shell, then the energy of this third one, it will be higher than the first and the second one. So it means that as we move away from the nucleus, then the energy of the shells, it is going to increase, right? And over here I just talk about the single atom, and when we talk about the single atom, then we talk about the concept of energy levels, right? But if in a particular crystal, like if we have large number of atoms that are interacted with each other, right? Means like suppose if I have one one more chlorine atom, and the outermost shell of this chlorine, it is over here. So now these atoms of the second chlorine atom, they are going to interact with this electrons, right? Means the electrons of different atoms, they are going to interact with each other, due to which this energy levels now over here, this E1, E2 and E3, they just have a single value. Means suppose if the value of this is 0, electron volt, we like in this atomic level we talk about the energy in terms of electron volt. EV means electron volt, right? So if the energy of the innermost shell, if it is 0 electron volt, let the energy of this, let it be 1 ev, 0 ev, let it be 3 ev, and so on. Now when I say that the energy of this third shell it is 3 ev, it means that all the electrons in the third shell, means all the 7 electrons of this chlorine atom, all of these electrons will have the same energy of 3 electron volt. Similarly, all the electrons in the second shell, they will have the same energy of 1 electron volt, and so on. But when we have large number of atoms interacting with each other, in that case, this energy level, this energy level, they will convert into the bands. Why? Because when large number of atoms they are interacting with each other, then the electrons, these electrons that are present in the same shell, now these electrons will not have the same energy, because suppose if this electron, if it is interacting very closely with the electron of another atom, right, whereas the second one, it is not that much interacting with the electron of the another atom, in that case the energy of this, it may be different from the electron of this, because both are interacting with the neighboring atoms in a different way, right? So it means that instead of a label, we call it as discrete labels. Instead of discrete labels means having a same value, we will be having a bands means that the electrons in a particular shell, they will have the energy in some range, right? For example, suppose if it is 3 electron volt, then after interacting with a large number of neighboring atom, this 3 electron volt, the range can be in between 3.5 to 2.5 to 3.5 electron volt. So what I am trying to say, that instead of having a single value, we will be having a bands, right? And the electrons in the third shell, they may have any energy value in between this range, right? Remember that over here, this 2.5, 3.5, this 1 electron volt, I just assume this value. These are not the exact value that are for the chlorine, right? So overall, instead of energy levels, we will be having a bands, right? We will be having a bands. And when we talk about the bands, and especially when we are talking about the interaction, then the interaction of the outermost shell, interaction of the electrons in the outermost shell is only important, because the electrons in the innermost shell, means in this second shell and the first shell, they cannot form any covalent bond, they cannot form any bonding with any neighboring atom, right? So only the electrons in the outer shell, they have that capability, right? So over here, when we talk about the conductivity, like when we talk about the whether the electrons will be there, free electrons will be there in the material or not, in that case we just want to know about the condition of the outermost shell, right? So the energy bands, like the energy levels, they are converted into energy bands, and finally what we will get a band which is known as a valence band. This valence band, it is the outer or the outermost, it is the energy band of the outermost shell, or the energy band of the outermost shell, right? So the valence band, we call the energy band of the outermost shell, we simply call it as a valence band, right? And valence band means that the electrons that is present in the outermost shell, right? Now apart from this valence band, we also have one band which is known as a conduction band. And as the term like conduction band, and as you may be like this word conduction, that the current is conducting, electrons are flowing. So conduction band is the energy band. If electrons are there in this conduction band, then only the electrons are considered free, right? So the electrons in the valence band, electrons in this outermost shell, they may be free or they may not be free, right? They may be free or they may not be free. If they are free, then it means they will be present over here in the conduction band. So if the electrons are free electrons, then the electrons will easily move to the conduction band, right? And the energy, if we talk about the energy, then the energy of this EC. So the energy of EC is always higher than the valence band. Means the electrons will be free when the energy of the electron is quite large, so that the electron can this electron can free itself and can detach from this atom, chlorine atom, right? So if the electron has that much amount of energy that it can detach itself from the atom, then it means that that electron will be in the conduction band. And if the electron is in the conduction band, then it means that the electron can make current, like current can flow. So to have a current, we should have the electrons in the conduction band, right? Now if we look at these three board models for the conductor, for the sodium, for the silicon which is a semiconductor, and for a chlorine which is an insulator. If we look at these three, now the total number of electrons in sodium, it is 11. In silicon it is 12, it is 14, and in chlorine it is 17. And you can see that all these three elements, they have three shells, right? They have three shells. Now like as I told you, that we are more interested for the outermost shell, right? Now in the outermost shell of the sodium, we just have one electron, right? And as per the chemistry that we have discussed that we know from our school is that since we have only one electron in the outermost shell of this sodium, so this particular electron, it will be very less amount of energy is required to detach this electron from this atom. So this electron can free itself very easily. Means just at a room temperature, this electron will find itself free, detached from this atom, right? Because very less amount of energy is required for this electron to detach from the atom. Whereas if we talk about the chlorine insulator, then in the outermost shell we have 7 electrons. And now this 7 electrons in the center, at the center we know that we have positive charges. So 17 positive charges, they are attracting all these electrons. So since 17 positive charges are there, so it will be quite difficult for these 7 electrons to detach themselves. Means very high energy is required to detach this electron from the outermost shell. And it is the reason that insulators, in the insulator, we do not have free electrons. And since we do not have free electrons, so current cannot be there. And it is the reason that if we are standing on an insulator, then we do not feel any electric shock, because current cannot flow through the insulator. Means that the energy that is coming through the current, that energy is not also capable to detach these outermost electrons from the atom, right? So since these 7 electrons, they are tightly bounded to its nucleus, right? Now if we talk about a conductor, so any element having less than 4 electrons in the outermost shell, if there is any element that has less than 4 electrons in the outermost shell, then it forms a conductor. It means less than 4 means that the atom can have 1 electron, 2 electrons, or the 3 electrons, right? And in all these 3 cases, the electrons, they are quite free and they can easily detach themselves from the nucleus, right? If we talk about the insulator, so any element having number of electrons greater than 4 electrons, means in the outermost shell, if the element has greater than 4 electrons, means 5, 6, 7, right? So if the element has 5, 6 or 7 electrons in the outermost shell, it means that the element is an insulator, and it is difficult, quite difficult, to detach those electrons away from the atom, away from the nucleus. Now if we talk about the silicon, now in the silicon we have 4 electrons in the outermost shell, in the outermost shell, and means 4 means it is in between the conductor and the insulator, right? So as I told you that very less energy is required in conductor to detach the electron, whereas very high energy is required to break the electron, to detach the electron from the nucleus. Now since the semiconductor, it is in between the two, so it means like medium energy is required, medium energy is required to detach these electrons away from the from the nucleus. And somehow if we are able to detach these electrons, then it means that we can make, like, current can be established, right? So over here, if we talk about, if we discuss this with respect to the energy band, then the energy band, like as I told you, that in the energy band we have 2 bands. First is conduction band, another is valence band, right? And in this band we have a gap. Gap means, like, this is energy of the valence band, this is energy of the conduction band. Now the difference energy gap, so the energy gap is energy gap, it is EC minus EV. Means energy gap means that if there is any electron over here, then this electron need EC minus EV energy to move from valence band to conduction band. So if somehow if the electron is able to get this energy, then the electron will move to the conduction band, right? And this amount of energy, it is known as energy gap, or we also call it as forbidden gap. And in this forbidden, like within this energy gap, no electrons are present within forbidden gap, right? Means and electrons can exist either in valence band or in the conduction band. They cannot stay in between that, right? So if suppose if electron is trying to move, if electron got some energy and electron try to jump from valence band to the conduction band, but if that energy is not greater than this energy EC minus EV, then electron will jump up to this height, and from this height it will come back, because the energy is not sufficient, minimum that is required. So electron will try to jump, but if the energy is not that much equal to the energy gap, then it will come back to the valence band. Now if we talk about the energy band of this energy band, conduction band and the valence band of the conductor, now since as we discussed in the previous one that the outer shell electrons, they are free, and free means that they are free to move. Free to move means that they can establish the current. So it means that the valence band and the conduction band of the conductor, they are overlapped in such a way that if there is any electron in the valence band, then it is also present in the conduction band. So as such, no energy is required because the conduction band and the valence band, they are overlapped. It means the energy gap is zero. There is no gap in between the conduction band and the valence band of the conductor. And since there is no gap, so free electrons are there in the conductor, which are moving randomly even without any voltage supply. They are moving randomly. When we supply any voltage supply, in that case we just applied some force on the electron, and that applied force simply direct them to a particular direction, and due to that particular direction, current come into picture. Right, now coming to the insulator, as we discussed in the previous one that all the electrons in the outermost shell, they are tightly bounded, means very high energy is required to detach these electrons, to move these electrons from valence band to conduction band. It means that the valence band and the conduction band, this gap is too high. This gap, energy gap, it is too high, and typically, like for the insulator, typically this gap is of the range 5 or 7 electron volt, means, and this is too high, right? So it is quite difficult, like we have insulation breakdown, right? But it is quite difficult to detach these electrons from the nucleus and to make them these electrons, to move these electrons to the conduction band. Now when we come to the semiconductor, now since the energy, as we discussed earlier, that in the semiconductor the energy that is required to detach this electron from the nucleus, medium energy is required. So medium energy means that the energy gap between the valence band and the conduction band, this energy gap, it will be medium. Means like in the insulator case we are hopeless, means we can hopeless in the sense that we cannot move free electrons from valence band to the conduction band. But in this silicon, the energy gap is medium, and there is some hope in the sense, like if I talk about silicon, so the energy gap of silicon, it is of the range like 1.1 electron volt, whereas for a germanium it is simply just this, it is simply 0.67. So you can imagine, you can see the difference between the energy gap of the semiconductors and the energy gap of the insulator. And it is because of this energy gap that the semiconductor somehow, like we can provide some energy, some external source of energy can be provided to the semiconductor, and so that the electrons that are present over here, they may move to the conduction band. And once these electrons are available, once this electron move to the conduction band, right, so this electron will then start flowing and they establish a current. Means the material which seems imperfect, which seems that it is not a conductor and cannot, like current cannot flow through it, but when due to some external energy, these electrons can move from valence band to the conduction band. And once that external energy is provided, then this semiconductor can behave as a conductor. And now that external energy, we need to provide some external energy, and that external energy gives us the power to control the semiconductor devices. Apart from this, there are other things also that due to which we are able to control the semiconductor devices. So but this is also one of the thing that, like some of the semiconductor devices, they are sensitive for the light. Means if light, when light falls on the, like solar panels, like the solar panels, in the solar panels, in the solar panels in the solar panels, the electrons in the solar panels, we have the semiconductor devices, right? We have the semiconductor material, and in that semiconductor material, when the sunlight falls on that material, then with the help of that sun energy, photons, we get the photons. So due to that photons, these electrons in the valence band, they receive the energy and they are able to move to the conduction band, and once they are able to move to the conduction band, then they forms a current, and the current formation in the solar panel is then taken to the device or to the battery to store, right? So you can imagine the power of this semiconductor material, right? We have large number of sensors that are designed as like light sensitive diodes, right? So we have large number of devices that can be that are available, and that is just because of this controlled conductivity of the semiconductor materials, right? Now after this, now I am going to discuss the comparison of the germanium and the silicon, right? So over here you can see that in the germanium we have 4 valence bands, whereas in silicon we just have 1, 2 and 3, right? So you can now imagine, over here the nucleus, in this nucleus we have like 2 plus 8 plus 18, so total of 28, right? Plus 4 electrons are in the outer shell, so total of 32 positive charges they are attracting, they are like making these electrons, all these electrons, they are tightly bounded due to this 32 positive charges present in the nucleus, right? But since there are in the germanium there are 4 shells, so the energy, these electrons in the outer shell of the germanium, they are less tightly bounded, uh, they are less tightly bounded in comparison to the silicon, because silicon, this third shell, it is quite close to the nucleus, due to which these electrons, they are tightly packed in comparison to this outermost electron of the germanium, which is in this 4th shell. So it is due to this reason, that the energy gap of germanium, it is less than the energy gap of the silicon, right? Because as we know the concept of energy gap means that how much energy is required to move the electron from the valence band to the conduction band. So since this outermost electron of the germanium, since they are in the 4th shell and hence they require less energy, so less energy, the energy gap of germanium will be less in comparison to the silicon, which is in the 3rd shell and hence tightly bounded to the nucleus, right? So similarly, now since the energy gap of germanium is less in comparison to the silicon, so now you can imagine that if we talk about a room temperature, or if we just increase the temperature, then what happened? Due to that increase in the temperature, due to the heat energy, these electrons, they get the energy, and the outermost electrons, they get detached, right? Now since the energy gap of germanium, it is less than the silicon, it means that for the same amount of energy, if we provide same amount of energy to both of this molecule, means of this crystal of germanium and the crystal of silicon, if we provide the same energy to both of them, in that case, since the energy gap of germanium is less, so it means more electrons will be detached, right? It means suppose we know that it is, for germanium the energy gap is 0.67, but let me take it as 0.5 just to for a round off, and for silicon it is 1.1. For a round off, let me take it as 1 electron volt. Now suppose means 1 electron volt and 0.5 electron volt. Now suppose if somehow we get 10 electron volt energy, so with 10 electron volt energy, with and 1 electron need this, so it means 20 electrons will be able to detached, whereas for a silicon only 10 electrons, with this requirement of energy for 1 electron, 10 electrons will be able to get detached, right? So you can see that only 10 electrons in silicon and 20 in germanium. So with the same amount of energy available, more electrons can get detached from the germanium. So we can say that the free charge carriers in germanium, it is greater than the silicon. It is greater than the silicon, right? So, and the reason is obvious, because the energy gap of the germanium, it is less than the silicon, and for a germanium, the number of free charge that are available at room temperature, it is 2.5 10 power 13, whereas for silicon it is 1.5 into 10 power 10. So approximately 1000, like germanium has 1000 times more, approximately 1000 times more free charge carriers in comparison to the silicon. Apart from this free charge carriers, now one more thing is there about the conductivity. Now we know that in a metal, when we increase the temperature, resistance decreases when temperature increases, right? If the temperature is increased, resistance decreases in metal, right? And the reason was that when the temperature is increased, then the atoms, they vibrate, and due to the vibration, the free electrons that are moving, they got an obstruction from the positive ions that are present, and due to the vibrations of the positive ions, free electrons, they got obstruction, due to which resistance increases. With temperature increase, resistance increases. But in case of semiconductor, it is different. In semiconductor, when the temperature is increased, then resistance decreases, or we can say, or conductivity increases. Now why? How does it happen? Because both semiconductor and the metals, both have the positive ions, both have the electrons, right? Then why this difference? The difference is that in the metal we have free hand electrons available. We do not need any external energy to generate the free electrons, right? So when the temperature is increased, only resistance is increasing. But in case of the semiconductor, with the increase in temperature, these vibrations, obstructions by positive ions increases, but at the same time, free charges, as we discussed in the previous slide, that free charges they are going to increase, right? So in semiconductor, when the temperature is increased, electrons in the outermost shell, they got the energy, and due to that energy, free charge carriers also increases, and due to the free charge carriers that are increased, due to the increase in their number, the conductivity, the conductivity means the conduction of the current will be increased, and overall the resistance will be assumed to be decreased, right? Because in the when the temperature is not increased, in that case there was the semiconductor does not have any free charge carriers, and if there is no free charge carrier, then the conductivity will be zero. With the increase in temperature, along with the obstruction, we also have the free charge carriers. So due to that increase in the free charge carrier, the resistance or the conductivity increases, right? Whereas in the metal already has the free charge carrier, so the only addition is the obstruction to the free charge carrier. So it is the reason that in the metal the resistance increases and the conductivity decreases in the metal, right? So this we have already discussed, and this conductivity and resistivity. And we also know that the resistance, it is this rho A by L, where this rho, it is the resistivity. And we also know that conductivity, it is inversely proportional to resistivity, right? So in semiconductor, when we say that with the increase in temperature, this conductivity increases, it means the resistivity decreases, right? So over here like if I look at this table, if you look at this table, so over here I mentioned about the free charge carriers, energy gap of a conductor, it is 0. The energy gap of a semiconductor is 0.67 for germanium, 1.1 for the silicon, and for the insulator it is greater than 5. And accordingly, as we already discussed, intrinsic material at room temperature, for a conductor we have large number of free electrons available, whereas for a semiconductor germanium we have this 2.5 into 10 power 13, for silicon it is 1.5 into 10 power 10. For insulator we have 0 charge carrier, and due to the 0 charge carriers there will not be any current. Now when we talk about the resistivity, then in the conductor we are going to decrease with temperature, with the increase in the resistance. Now whereas the resistivity of this germanium, you can see that resistivity of this semiconductor, it is germanium, it is just 50, whereas of silicon it is 10 power 3, which is again this 10 power 3, it is quite less in comparison to the resistivity of the conductor. And this difference, 10 power 6 and 10 power 3, this difference in the resistivity indicates that with the increase in the temperature, the conductivity of the semiconductor is going to increase. The resistivity is not much, even if it is 10 power 3, but it is less than the conductor. And since it is less than the conductor, so with this 10 power 3 resistivity, still the the conductivity is going to increase for the semiconductor, right? Whereas for the insulator, the resistivity is too high. Resistivity means high, means huge obstruction, and it is due to this reason that current cannot flow through the insulator. Now with this, now we come to the last slide, which is the intrinsic semiconductor. Now the intrinsic semiconductor are those semiconductors that have a very low level of impurities. Means, like we talked about silicon and germanium, right? But when we extract that silicon and germanium crystal, the purity of that crystal, that purity of that silicon and germanium crystal, it is like we need highly pure semiconductor, right? So if the semiconductor is pure, free from all the impurities, means the impurity is very very low, in that case we call that type of semiconductor material as intrinsic material, right? And when I say very low, ideally we need zero impurity. But when I say very low level, it means as per the technology, like whatever technology we have available presently. So as per that technology, whatever minimum is possible, at least we should try to achieve that. So with that minimum impurity, the semiconductor that we achieved, it is known as intrinsic material. Ideally, intrinsic material does not have any impurity. The impurity, it is zero, right? Now why we are talking about low impurity or zero impurity? The reason is that the low impurity level, it is really necessary. Why? Because the addition of one part of impurity per million in a silicon material can change the conductivity of a material from poor conductor to a good conductor. What it means, now presently, first of all, we need to make the semiconductor material as pure, means free of impurity, zero impurity is required. After that, we are going to add the impurity, means when we are going to add the impurities, we are going to add the impurity in a controlled manner, means it will not be like any amount of impurity. We are going to add the impurity in a very controlled manner, something like one part impurity per million in one wafer of silicon, right? So very 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 less impurity we are going to add to the to the pure silicon, means to the intrinsic semiconductor material we add impurity according to us, and in that way we are going to control the conductivity. As I told you that with the help of semiconductor we can control the conductivity, right? So by, if we already have the impures, if our semiconductor material is impure and we do not know about the exact amount of impurity, then we, like, there will not be any use to add the impurity, right? We will not be able to control. But if the initially, if the semiconductor material is pure, and thereafter when we add the impurity in a controlled fashion, right, then we can control the conductivity as per our requirement. So it is the reason that we need the pure semiconductor material. We need to start with the pure semiconductor material, pure semiconductor wafer, right? Wafer means a complete crystal silicon plate, or the silicon plate of a crystal, it is known as wafer, right? And all this, that whatever we have discussed, it is it over here we discussed everything with respect to the intrinsic semiconductor material. Because we have not talked about the impurity, we consider that the impurities are not there in the semiconductor material. So because in the starting we need to discuss the idealistic things, right? So all these things, all these numbers, they are for the intrinsic semiconductor material. In the next lecture I will start with the extrinsic semiconductor material. So if any of you have any doubt, you can ask me, and you can put it in a comment box of the